Welcome to the second lecture on using GNATprove to perform program analysis. This lecture presents the second type of analysis available, which is used to perform proof of program integrity. For its soundness, this analysis relies on the prerequisite of having performed flow analysis, and a user should not proceed further if there are still unanswered flow analysis messages for their program. The primary objective of performing proof of program integrity is to ensure the absence of any runtime error during the program's execution. There is always the potential for errors which can occur at program's execution, but will not be detected during compilation. These errors, called runtime errors, are those targeted by GNATprove's analysis capabilities. There are various kinds of runtime errors, including array out-of-range access, subtype range violation, overflows in computations, and division by zero being the most common. Taking a look at the code on this slide to give an example, let's look at a simple assignment statement setting the value of I plus jth cell of an array of naturals A to P divided by Q. If we do not know the values of I, J, P, and Q, then there is a question of what are the errors which may occur when executing the code. In fact, there are quite an important number of them. First, the computation of I plus j may overflow, for example if I is integer tick last and j is positive. Then, its result may not be in the range of the array A. On the other side of the assignment, the division may also overflow, but only in the very special case where P is integer tick first and Q is -1, because of the asymmetric range of signed integer types. As the array contains natural numbers, it is also an error to store a negative value in it. And finally, the division is not allowed if Q is the value 0. For all those runtime errors, the compiler will generate checks in the executable code to make sure that no inconsistent state can be reached, raising an exception if those checks fail. You can see the type of exceptions raised due to failed checks for each of the different assignment statements on this slide. Note that these runtime checks are costly, both in terms of program size and execution time. They do not come at zero cost, and therefore, depending on the context, it may be appropriate to remove them if we can statically ensure that they can never be needed at runtime. This is where analysis using GNATprove can be used to demonstrate statically that none of these errors will ever occur at runtime. More precisely, GNATprove logically interprets the meaning of every instruction in the program. Using this interpretation, GNATprove generates a logical formula and a named verification condition for each possible check that implies the validity of the code. The verification conditions will then be given to an automatic prover. If every verification condition generated for a program can be validated by a prover, it means that no error will ever be raised at runtime when executing this program. For scalability reasons, GNATprove performs proof of program modularity on a per subprogram basis. To do this, it relies on pre- and post conditions to properly summarize the input and output state of each subprogram. More precisely, when verifying the body of a subprogram, GNATprove assumes it knows nothing about the possible initial values of its parameters and of the global variables it accesses except what is stated in the subprogram's precondition. If no precondition is given, then no assumptions can be made. For example, the code on this slide shows the body of increment can be successfully verified as its precondition constrains the value of its parameter x to be less than integer tick last. In the same way, when a subprogram is called, GNATprove assumes its out and in-out parameters and the global variables it writes can be modified in any way compatible with its post condition. For example, increment shown here has no post condition, Therefore, GNATprove does not know that x is smaller than integer tick last after the subprogram call. Therefore, it cannot prove that the following addition cannot overflow. There are two cases where modularity is not enforced by GNATprove. First, local subprograms without contracts can be inlined if they are simple enough and they should not be recursive or have multiple return points. If we remove the contract from increment in our example shown here, then it fits the criteria for inlining. GNATprove sees the call to increment exactly as if the increment on x was done directly. Therefore, it can verify successfully that no overflow may occur on either of the subsequent additions. The other case concerns expression functions. If a function is defined as an expression function with or without contracts, then it is handled as if it had a postcondition stating the value of its result. In our example, replacing increment with an expression function allows GNATprove to verify successfully the overflow check in the following condition. Though they are perfectly suited for formal verification, Ada 2012 contracts are primarily designed to be checked at runtime. Code that verifies the contracts at runtime can be generated by the compiler using the appropriate switch, which is -GNAT-A. If an Ada 2012 contract does not hold at a given subprogram call, an exception named assert_failure will be raised. This is particularly convenient during development and testing, but execution of assertions, and in particular preconditions, may also be retained during the program's deployment to avoid reaching an inconsistent state. For example, given our code here, if called on integer tick last, increment will fail before its body is even started, possibly avoiding an inconsistent modification of the global state of the program. In the same way, any call to the badly implemented absolute function on anything else than 0 will fail before the caller can be badly impacted by receiving a negative value. This early detection of failure allows an easier recovery and facilitates debugging. To ensure the soundness of its analysis, GNATprove needs to statically verify pre- and postcondition contracts. Like in the runtime semantics of contracts, preconditions are verified every time a subprogram is called. Postconditions, on the other hand, are verified modularly once and for all as part of the verification of the subprogram's body. In our example shown here, GNATprove will detect both the identified errors as soon as they are visible. For the precondition, it has to wait until increment is improperly called, as a precondition is really a contract for the caller. On the other hand, it does not need absolute to be called to detect that its postcondition does not hold on all of its possible inputs. In Ada 2012, expressions in contracts have the regular semantics of Boolean expressions. In particular, runtime errors may occur during their computation. To facilitate both debugging of assertions and combination of testing and static verification, the same semantics is used by GNATprove. During proof of programs, it makes sure that no error will ever be raised during the execution of the contracts. This semantic may sometimes be considered too heavy, in particular regarding overflow checks. For example, we tried specifying an appropriate precondition for the function add that would avoid overflows in its body when computing the addition of x and y. Unfortunately, as expressions in assertions have the regular Ada semantics, GNATprove complains that an error may be raised while checking add's precondition. This is legitimate, as we may see by calling add on integer tick last and 1. On the other hand, depending on the context, we may have preferred to have GNATprove use the mathematical semantics of addition and properly verify that no error will be raised at runtime in the body of the subprogram add. This behavior may be obtained by using a compiler switch named -GNAT-O, which allows to independently set the overflow mode in code and assertions to either reduce the number of overflow checks or to completely eliminate them. Note that this switch will also make the compiler avoid overflows at runtime. As we have seen, contracts are a key feature for GNATprove. It supports pre- and post-conditions, as well as assertions introduced by the pragma assert and type predicates. New contracts have also been introduced for the process of formal verification. For example, the new pragma called assume is handled as an assertion at execution, but introduces an assumption for proof of program, that is, a Boolean expression which is assumed to be true by the tool without any verification. This is useful, but must be used with great care. Another construct introduced for GNATprove is the contract cases aspect. It allows to specify the behavior of a subprogram by a disjunction of cases. Each element of a contract cases aspect is in fact a small contract made up of a guard which may only reference the subprogram's inputs and is evaluated before the call and as a consequence. At each call of the subprogram, there must be one and only one case for which the guard evaluates to true. The consequences of this case is the only one that should hold on exit. In GNATprove, validity as well as disjointness and completeness of the contract cases are verified only once in the context of the subprogram's precondition. If GNATprove reports an error while verifying a program, it could be for various different reasons. There may be an error in the program, the property may not be provable because of some missing information, or the prover used by GNATprove may be unable to discharge a perfectly valid verification condition. The remainder of this lecture is dedicated to the sometimes tricky task of debugging failed proof attempts. First, let us look at the case where there is indeed an error in the program. Here we see there are two possibilities. The code may be incorrect, or, and it is equally likely, the specification may be incorrect. As an example, there is an error in our procedure incre_until, which makes its contract cases unprovable. As assertions can be executed, it may help to test the program on a representative set of inputs with assertions enabled. This allows bugs to be found both in the code and in any contracts. For example, given the subprogram here, testing incre_until on an input bigger than 1000 will raise an exception at runtime. It specifies that the first contract case is failing, which means that incremented is true. Still, if we print the value of incremented after the call, we will see that it is false, as expected for such an input. Indeed, guards of contract cases are evaluated before the call, and our specification is erroneous. To correct this, we should either put x to be less than 1000 as a guard of the first contract case, or use a standard postcondition with an if expression instead. Even if both the code and the assertions are correct, GNATprove may still generate an unprovable verification condition for a property. This may happen for two reasons. First, the property may be unprovable because some assertion is missing in the code. In particular, this can be induced by the modularity of the analysis, which causes a tool to only retain explicitly annotated properties. Second, there may also be some missing information in the logical model of the program used by GNATprove. This is especially likely for difficult to support features such as floating point arithmetic or string literals. As an example shown here, the verification generated by GNATprove for the postcondition of the increase subprogram is unprovable. It states that if its parameter x is smaller than a certain value for c, then its value will be increased by the procedure, whereas if it is bigger, its value will be saturated to C. When used with the appropriate options, GNATprove can provide additional information on a failed verification condition. In particular, if the condition is complex, it can locate precisely the part of the condition which is failing. For the example shown here, GNATprove states that it cannot prove that x is equal to c, which means that we are in a case where x is greater than c. Another additional information may help the code review. If it is used inside GNATbench or GPS, GNATprove can highlight the path in the program leading to a failed condition. Here it is the first branch of the if statement. As a consequence, we know that GNATprove cannot prove the postcondition of increased subprogram when both x is greater than c and x is smaller than 90. Indeed, in this case, our postcondition does not hold. But maybe we did not expect the value of c to change, or at least not to go below 90. In this case, we would simply state so by either declaring c to be constant or adding a precondition to the increase subprogram. Finally, there are cases where GNATprove provides a perfectly valid verification condition for a property, but it is not proved by the automatic prover in the latter stages of tool execution. This is quite a common occurrence. Indeed, GNATprove produces its verification conditions in first-order logic, which is not decidable, especially in combination with arithmetic. Sometimes the automatic prover just needs more time, but also sometimes the prover will abandon the search almost immediately or loop forever without reaching a conclusive answer. For example, in the code shown here, the postcondition of our GCD subprogram, which calculates the value of the GCD of two positive numbers using Euclid's algorithm, cannot be verified with GNATprove's default settings. The first thing to try is to increase the maximum amount of time that the prover is allowed to spend on each verification condition. You can do this using the option --timeout of GNATprove. In our example shown here, bumping it to 1 minute, which is relatively high, still does not help. We can also specify an alternative automatic prover if we have one. This can be done using the option --prover of GNATprove. For our postcondition, we have tried both the Z3, the alt-ergo, and the CVC4 provers without any luck. To better understand the problem, we have added intermediate assertions to simplify the proof and pin down the part that was causing the problem. This is often a good idea when trying to understand by review why a property is not proved. Here, provers cannot verify that if A minus B and B can be divided by result, then so does A. This may seem surprising, but nonlinear arithmetic involving multiplication, modulo, or exponentiation, for example, is a difficult topic for provers and is not handled very well in practice by any of the general purpose provers like alt-ergo, Z3, or CVC4. That concludes the slides section of this lecture, and we shall now move on to the quiz section. Please review the code on this slide and click the yes tick icon if you believe the code is correct. Otherwise, click the line of code you think is wrong. Once you have made your selection, please click the Submit button. Here is the correct answer to the question. Once you have understood the answer, please click anywhere on the slide to proceed to the next question.
This concludes this current lecture. We'd like to welcome you back to the Ada University in the future to further your knowledge of Ada programming language and Spark. Thank you for your attendance.